Hi, my name is Theo, and I'm a fifth-year PhD candidate in Matt McHenry's lab, and today I'll be talking about the locomotion of sea stars. So sea stars have these 2 feet that are located on the oral side or the bottom side of the animal, and these 2 feet are hydraulically powered. They exert a force on a body during locomotion. And a single sea star can have up to hundreds of these 2 feet among the 5 arms. And sea stars coordinate these 2 feet to perform a variety of different behaviors, one being the bouncing gait. The bouncing gait is characterized by a vertical oscillatory motion relative to the ground, and the sea star doesn't have a brain. So we became interested in how these feet are actually coordinating or synchronizing with each other during the bouncing gait. So let's take a closer look at the bottom view of the animal to see what they're doing. So the sea star actually starts out crawling at a slower speed, and eventually it transitions in this type of bounded running that we call the bouncing gait. And unlike in crawling, the feet are synchronized in the power strokes during a bouncing gait. And we saw that about a third of the feet are engaged in a power stroke during a bouncing gait, meaning a third of the feet would attach and detach at similar times during a bouncing gait. And again, the sea star doesn't have a brain, and we're interested in how these feet are actually synchronizing with each other. And one way that the feet are synchronizing with each other is via nervous coordination. So, for example, this nervous system sends a motor command to a group of 2 feet to attach, and another motor command for that same group of 2 feet to detach from the surface they're walking on. But since this is such a simple nervous system, and there's so many 2 feet, it is conceivable that the 2 feet are synchronizing with each other via mechanical coupling, also known as Huygens synchronization. So here is a classic physics example where metronomes all start out at a random initial orientation, and eventually they synchronize with each other. And this is because they're mechanically coupled to a same moving surface. And the question we are posing is mechanical coupling sufficient for synchrony in sea star 2 feet? And our approach to this problem is that we first made a numerical model, and we compared our kinematics of our model to our animal, and then we performed the same experimental manipulation on both the animal and our model. And we also developed a robot to show the same concepts. So let's dive into our numerical model. A numerical model has 2 feet, and a single 2 foot is represented by 2 springs, a linear spring and a torsion spring. The linear spring exerts a linear force, and the torsion spring exerts a rotational force or a torque. And many of these feet exert a force on the center of mass of the body, where the submerged weight and the damping force are accounted for. And similar to the metronomes I showed you in the previous slide, our model does not have centralized control for synchrony, and the feet also all start out at a random initial orientation. Here is our simulation of our model, and our model has 250 feet, and you can see that it also bounces with synchronous feet. And again, our model does not have centralized control for synchrony, meaning there's no motor command to tell the feet to attach at the same time or detach at the same time. And the synchrony is due to the mechanics of the system. Taking a look at the data from our model, we can see that in the vertical body position, there's that bouncing behavior I was talking about. And we also looked at the foot angle. And this is the foot angle relative to the direction of motion and the surface that the feet are attaching to. And in this foot angle, we saw that there was a sigmoidal pattern where at the beginning of the power stroke, that foot angle is large, and as the power stroke goes on and the body is vaulted over the feet, the angle becomes small. And since groups of 2 feet are engaged at a similar angle at the same time, this is evidence that the feet are synchronizing with each other. And comparing our model to our animal, we saw that there's also bouncing in the animal in the vertical body position, and the foot angle has a similar sigmoidal pattern. So to answer the question, is mechanical coupling sufficient for synchrony? Yes, in theory, because our model without centralized control bounces with synchronous feet. Now that we've established a relationship between the mechanics and the synchrony of the system, we wanted to test this relationship using an experimental manipulation. And our experimental manipulation is varying the submerged weight of the sea star. Here's a sea star bouncing along at about 130% of its original submerged weight. And the question we're posing is, what are the effects of a change in submerged weight on the synchrony of sea star 2 feet? And we not only increased the weight to 150% of the original submerged weight by adding weights to their backs, we also decreased their effective submerged weight to about 50% of the original submerged weight by affixing floats onto their bodies. And we saw that the proportion of feet that were engaged in a power stroke during bouncing increases with an increase in submerged weight. So in other words, more feet are recruited at higher weights. And this resulted in the bounce speed only decreasing slightly despite this large range of submerged weights that we tested. So comparing our animal data now to our model data, we saw that the bounce speed also decreased with an increase in submerged weight. And in our model, more feet are also recruited at higher weights. So how does this happen? Our model doesn't have centralized control for synchrony. Since this is a numerical model, we're able to take a closer look at a couple of different variables more closely, and one of them being the force of the feet. And we saw that the submerged weight creates a force threshold that the feet have to overcome before the body can move. So as the body lifts up, enough feet have now been gathered to generate a force that is higher than the force threshold in order to move the body forwards and upwards. And this is a time series of our model bouncing at 75% of its original submerged weight. And when we increased the submerged weight to about 125%, we saw that more feet are now recruited due to the higher submerged weight. So to answer the question, what are the effects of a change in submerged weight on the synchrony of sea star 2 feet? We saw that when we increase the submerged weight, this increased the force threshold, which then resulted in more feet being recruited. So the weight acts as a mechanical perturbation that increases the synchrony of the system. We wanted to show this in a robot. Here is our robot. It is just 10 velocity-controlled servos affixed onto an acrylic chassis. And the only control that the servos are getting is that they all start out at a random initial orientation, and then we set them all going at the same velocity. So there is no centralized control that tells the servos when to come in contact and when to not come in contact with the ground. And a question we're posing is, what are the effects of a change in weight on the synchrony of the servos in a robot? And this is the same question we posed for our animal and also our numerical model. And here is our robot unweighted. You can see that groups of 2 feet are synchronized with each other, and the robot also bounces. And when we weighted the robot down with a bag of rocks, now all of the servos are engaged with each other in order for the robot to bounce. And we ran some trials of the robot weighted down and unweighted, and we saw that there was a significant difference in the maximum number of servos that were engaged during a power stroke when we weighted the robot down compared to when the robot was unweighted. So when we weighted the robot down, the robot engaged between 9 and 10 feet, and when the robot was unweighted, it engaged between 5 and 10 feet or 5 and 10 rows. So again, we showed that the weight is a mechanical perturbation that increases the synchrony of the system. Overall, in summary, is mechanical coupling sufficient for synchrony? Yes, in both our model and robot without centralized control, bounced with synchronous feet. What are the effects of a change in weight? We saw that in our animal, model, and our robot, when we increased in weight, the number of feet that were engaged also increased. And in our model, we were able to see that when we increased the weight, this increased the force threshold, which then resulted in more feet being recruited. And some future directions on our robot, we are planning on implementing accelerometers and force sensors in order to collect velocity data and also force data. So overall, we can say that collective control creates response to loading. And this type of collective behavior isn't only seen in sea stars, it is also seen in groups of ants and also molecular motors, where it's a multi-agent system that increases the number of agents involved as the load gets heavier. Our integration of robotics, mathematical modeling, and also animal experimentation has emphasized the importance of mechanics in animals and robots that have simple nervous control but complex motions. And by identifying these simple algorithms that can control multi-agent systems in a coordinated fashion, we can decrease the computational power that is needed for complex robots. And with that, I would like to thank those that have made these projects.